Thanks for the introduction. So at first, thank you for the opportunity to speak here. And so, yeah, I want to speak about the polarization types of Lagrangian fibrations. So maybe if I say Lagrangian fibration, I mean a Lagrangian fibration on an irreducible holomorphic symplectic manifold, or hyperkähler manifold, as Giovanni prefers to call them. So let me fix the standard setting for the talk. So X will be always an irreducible holomorphic symplectic manifold. So for short, just IHS. Or sometimes I also say, like Giovanni, hyperkähler manifold. So, and what I mean by a polarization type is basically a new deformation invariant for Lagrangian fibrations. And I have to explain what this means. So let me give you a short introduction to Lagrangian fibration. And the best way to do this is maybe just give you a result by Matsushita. So we have here holomorphic symplectic manifolds. So I denote by sigma the holomorphic symplectic form. So, and giving you the definition of a Lagrangian fibration, I just give you a result by Matsushita. And this is actually quite remarkable. So X will be always hyperkähler. So let F from X to B surjective holomorphic map. And I want it to have connected fibers. And B is just a normal complex space. And it should have not the trivial dimension and also not the dimension of X, which I always denote by 2n. So this is dimension of X, complex dimension. So then we have the following. The first part is we just assumed B a complex space, but it follows that it is projective. And the dimension of it is exact the half dimension of X, so n. So now comes the Lagrangian part. If we consider the fibers of F, so xt, which should be just a fiber over T, then this is a Lagrangian subspace. So this just means that if we take the holomorphic symplectic form and restrict it to the smooth part of this fiber, then we get just 0. And the last part of the theorem, if the fiber is assumed to be smooth, then, okay, this is actually not too deep. This is now an analogon of the Liouville theorem from real symplectic geometry. Then we get that xt is a complex torus, but indeed xt is projective, so a Abelian variety. So that the smooth fibers are Abelian varieties, so in particular projective, will play an important role later. Yeah, this is, so yeah, and such a map fx to b is called a Lagrangian fibrillation. And for short, I will just write LF. Yeah. So now one more thing is known about the base space B. And this is a result by Hang. So first is from Hang. So if we assume the base space B to be smooth, then it follows that B is just the projective space. And one more thing is to say, it's also important for the talk. It was shown by Markman that if X is of K through N type, then we know that this is the case. So B is also isomorphic to the Pn. Yeah? Okay. I want to consider polarization types. And now we know that the smooth fibers are Abelian varieties. And for Abelian varieties, we have the notion of polarization and the types. But before explaining you that, what I mean by polarization types of Lagrangian fibrations, I give you some examples. No, there's no example with a B singular known. So yeah, so the conjecture is that B is always smooth. Okay, let us look at some examples. So, and I mentioned 2. So if X has dimension 2, then it's a K3 surface. And also here, we have then Lagrangian fibration is the same as elliptic K3 surface. Yeah. So Lagrangian fibration are the natural generalizations of elliptic K3 surface to higher dimensional total spaces. And as you can also obtain a higher dimensional example if you start with elliptic K3. So let F S to P1 elliptic K3. So then we can look at the Duardi space of endpoints, or if you want, the Hilbert scheme of endpoints, Sn. Then take here the Duardi-Ballet map to the nth symmetric product of S, or Hilbert show map as you like it. And here you just take f times the map f to the n-symmetric product of the P1. But this is well known, this is just the Pn. So this is a Lagrangian fibration. And the generic fiber, yes, these are just products of, this is a product of elliptic curves coming from the elliptic K3. This is the most easy higher dimensional example. Okay, let me give you a much more, or not much more, but a bit more complicated example. This is were introduced by Bouville and generalized by Mukai. So they're called Bouville-Mukai systems. And here we have to start with a projective K3 surface. Okay. So let S be a projective K3, but we don't need the fiber structure. And then we choose a primitive Mukai vector of the form. So Mukai vector is always such a 3-tuple, and here we want to have 0. Here we want to be a nav divisor, and here any number. And this is just the element of the H0s plus H2s plus H4s. And I want that D is nav. So then general results of many authors, in particular Mukai and Yoshioka, imply that the moduli space of stable sheaves on the K3 F on S, such that the associated Mukai vector of the sheaf, so this is just the total Chern class of F times the Todd class of the K3, is given by this Mukai vector we have chosen. And this is it's an irreducible homomorphic symplectic manifold. And now we can easily write down a Lagrangian fibration on this manifold. So that I can erase? Okay. So we make the following construction. So I define a map pi from this moduli space to the linear system, or precisely the linear system, dual linear system of the divisor D. And here we take just a sheaf and map it to the support of it. And due to the chosen Mukai vector V, this is indeed well defined. And yeah, and here we have, again, this is a Pn, where 2n is d square plus 2. Yeah? And by construction, the generic fiber of such a Bouville-Mukai system is a Jacobian of a smooth curve. Okay. These are the examples I wanted to explain. And now let's come to the polarization type of the talk. So we know that the smooth fibers are Abelian varieties. And the first question is how to get a polarization of such a fiber. And this I can do by using observation by Voisin. So now let Fx to be a Lagrangian fibration. And we fix a smooth fiber. Smooth fiber xt. So, and Voisin has observed the following. Actually, she has not observed it, but she has written a proof where this fact follows. So, and this says that there exists a scalar class omega on our hyperscalar manifold X, such that the restriction of this scalar class to xt is integral, and it's primitive. Yeah, and in particular, this is also the reason why the smooth fibers are projective, so indeed Abelian varieties. And yeah, so such a class omega I call special. So precisely with respect to xt. So, but this has nothing to do with special scalar geometry. I just haven't found a better name for it. So we have a restriction of a scalar class to our smooth fiber xt, which is integral. So it in particular defines the polarization on this Abelian variety. So take such a omega. It is in particular, so omega restricted to xt is in particular a polarization on our Abelian variety xt. So now I just want to consider the associated type of it. So maybe I just recall the fact. So since xt is an Abelian variety, we have identification of the integral cohomology, which we can see as integer valued two forms on the homology. Yeah? So omega xt can consider as a two-form integer valued. So now the elementary divisor theorem says us in a good basis, we have the following representation of this two form. So we can write this as something like this. Where D is a diagonal matrix with integers d1 to dn, such that di divides di plus 1 and all integers di are positive. Yeah, and this is just the general construction of the polarization type of a polarization on a Abelian variety. Yeah, now I make the following definition. So df omega t defined as precisely these integers is called the polarization type of the Lagrangian fibration f x to b. Yeah, and now I say the polarization type, so I actually put here a statement that this indeed does not depend on the chosen special Kähler class omega and the fiber t, xt. Yeah? Yeah. Yeah. So in particular, the omega xt should be, where is that written? Should be primitive. Huh? So you know, yeah, the obvious theorem is, or actually not too obvious, but so df omega t does not depend on omega and t. Yeah, and let me give you the sketch of the proof. So this is actually applying to results of Matsushita and Voisin. So at first, let us just consider the restriction. So T is still the point of the base space. And from our hyperkähler manifold X, but now with real coefficients, to our fiber, still smooth fiber xt. So now the first step is you have to apply result of Voisin and then a result of Matsushita to see the following, that the object defined by the image of the restriction mapping of the Kähler cone of X intersected with the integral cohomology of the fiber is a semi-group of rank 1. So this has us, in particular, if we have chosen our smooth fiber, then the restriction of such special Kähler classes is somehow very unique if we want to take, at least if we take the primitive part. Yeah, now it's easy to figure out that if we let vary the t about over all smooth fibers, so the GT form a local system, G, for all t's, okay, let's say a local system on B0, which is thus defined, or it's just the subset of B parametrizing the smooth fibers. And yeah, this is, the subset is open in B and it is connected. And that it is connected is important for the third step. Yeah. So now we can write down a section of this local system which always hits the restriction of such a special Kähler class on all fibers. So it exists a unique flat section. Alpha from B0 to G. Here we can just write it down. So alpha t is defined as a unique primitive element in GT. Yeah, and this is exactly, so for every t, we hit exactly this the restriction omega xt. So we have that's the polarization type of the Lagrangian fibration. F omega t is computed as the polarization type in the usual sense of the polarization defined by alpha of t, but this has values in C to n, and the section alpha is in particularly continuous. So, and the BO is connected, so it must be constant. So it is constant. So this is alpha t, so this is a C0 map, C0 map. Since the B0 is connected. And what you can now do, you can think about it how it behaves under the deformation of the fibration. And so it's a deformation invariant. So if you consider a family of Lagrangian fibrations, so this just means we have such an S-morphism. And phi is a holomorphic map. And this should be a family of hyperkähler manifolds. And this is just some connected complex space. And this is a family of projective varieties. and we want that the restriction of phi to the hyperkähler manifold XS is the Lagrangian fibration. Yeah, or not in general. So if you consider here a family of K3 n-type manifolds, then it is, then the PS are always PNs, of course, by Matsushita. But in general, we don't know this. So yeah, and then in a similar proof I've just explained you can see the following, that the polarization type of the Lagrangian fibration of phi restricted to the hyperkähler XS is also, also does not depend on S in big S. So the polarization type is the deformation invariant of the Lagrangian fibration. Yeah, and now the question is how the polarization type behaves if we restrict to some deformation classes of hyperkähler manifolds. So let me give you one example. So I want pi from X to Pn, the Mukai system. And F should be just a generic fiber. Then we have two facts. The first one is, okay, I already told you that F is a Jacobian of a smooth curve. And the second more important fact, actually both are important, but the Picard rank of this generic smooth fiber is 1. So now we just know from the general theory that on such a Jacobian of a smooth curve, we have a principal polarization, and the Picard rank is 1. So with the special Kähler class, we had hit exactly this principal polarization. So these facts imply that the polarization type of every Mukai system is principal. And Mukai systems are in particular, so the X is a K3 n-type manifold. So, and Mukai systems, and the modular Lagrangian fibration, there are very many Mukai systems. So the conjecture was this, so in every Lagrangian fibration, X to B with X of K3 n-type, the associated polarization type should be principal. And this is what I've seen. The theorem is let X to Pn a Lagrangian fibration with X of K3n type. So I can now assume that the base space is Pn. So then the polarization type of it is principal. Yeah. And let me call this theorem star. Yeah, and now the question is how does for the other deformation types. And my general conjecture is that should be true. So not that this is principal, but if we have two Lagrangian fibrations, so that Fi xi to bi, I equals 1 or 2, be two Lagrangian fibrations, such that the total spaces x1 and x2 are deformation equivalent. So then the conjecture is the polarization types should coincide. So, and from the known examples of hyperkähler manifold, you can always deform to a hyperkähler manifold which admit a Lagrangian fibration. But the general statement is not known, but this nearly gives, so the polarization type nearly gives a new deformation invariant for hyperkähler manifolds, not only for the fibrations. Okay, the rest of the talk I want to explain you the proof of this result. And this follows mainly by methods Markman has developed. So what I want to do is, so let lambda be the K3n type lattice. And M0, a connected component of the moduli of marked K3n type manifolds. Okay, and then we can, with Markman's methods, we can describe a connected component of the moduli of Lagrangian fibrations with the total space always of K3n type. So we have the following. So let lambda in the K3n type lattice primitive and isotropic. Then the following U lambda defined as all marked pairs in M0, so in this fixed connected component of the moduli, with the following. At first, we want that there exists a Lagrangian fibration from X to Pn such that eta, so the marking, same definition as for K3 surfaces, and then the first Chern class of the pullback of F of the O1 bundle is just given by lambda. And this is a smooth hypersurface, and it is connected. So smooth hypersurface of M0 and connected. And in particular, it may not be Hausdorff, since the moduli of marked hyperkiller manifolds is not Hausdorff. And if we look at this connected component of the moduli of Lagrangian fibrations locally, then this U lambda, so locally, is given by the deformation space of the pair X and the pullback of O1. So the general modular space of Lagrangian fibration you can obtain by gluing such pairs, such deformation spaces of such pairs. So now the idea is, okay, we have a Lagrangian fibration fx to Pn, and it is contained in such a connected component, U lambda, and then we show that we have also in there a Bouville-Mukai system, and then this theorem implies that it must have the same polarization type of a Bouville-Mukai system, which is principal. Okay. Proof of star, and with star I still mean this statement. Okay, let X to Pn a Lagrangian fibration which with X of K3n type. So the first step is just choose the marking. Eta on X. And set lambda to be the eta of the first Chern class of the pullback of the O1 bundle. And actually with Fujiki's relation, you can see that this element is isotropic. And also that it is primitive. So this just means, so if we have chosen a connected component of the moduli of marked pairs, then this pair X eta is contained in U lambda. So now the second step is to use Markman monodromy invariance. And with them you can see. So this is just a technical tool to see when two pairs, or in our case, two Lagrangian fibrations, lie in the same connected component of the moduli. So with that, you can figure out that there's a Mukai system, pi x prime to Pn, with the marking eta prime, such that the eta prime also of the first Chern class of the pullback of the O1 is given by lambda. Yeah. So the pair x prime pullback of O1 is also in this connected component of the moduli. Okay. Yeah, and what you now do is so we have the following picture. You have somehow here our connected component U lambda. Somewhere we have our Lagrangian fibration x eta we started with. And somewhere here we have our Mukai system. Yeah, and then we just choose away from the between the points. And now Matsushita, the result of Matsushita gives local families over these points of Lagrangian fibrations. So local families of Lagrangian fibrations, let me call them phi k from xk to def k. So here we have like def 1, def 2, and so on, and we somewhere reach def n. Yeah, now, oh, sorry, these are, so they are parameterized by def k, of course. Yeah, now we are gluing the families to obtain a global family which both contains the both Lagrangian fibrations. Glue the phi k to obtain a family of Lagrangian fibrations containing f and pi. So, and then the result which I just erased there implies that the polarization type of F is given by the polarization type of pi, and pi is a Mukai system, so it's principal. Okay. And the obvious question is what we get for the other deformation types of hyperkähler. So let me give you this as the last statement. So conjecture. type of X and df. So if we think of a generalized comma type, then I think that the polarization type is 1, 1, 1, 1, and the last component is n plus 1. And this is actually due to an example of Saven. And if we look at the O'Grady 10 type, then this is also a principal polarization. And so O'Grady 6 type should be 1 to 2. And both the conjecture comes from examples of Mongardi and Wandel. Yeah, and currently I'm working on the generalized comma deformation type. Yeah, it's basically I've finished.